Technology for the benefit of humanity. So, we are IEEE Techverse Sri Lanka. One of the efforts launched by the IEEE Sri Lanka Section Student Activities Committee to inspire young people with technical breakthroughs. IEEE Techverse Sri Lanka has continued to offer information on many themes and trends linked to cutting-edge technology in the industry throughout last few years. With this continual heritage of giving society with knowledge about cutting-edge technology, we are delighted to begin the TechSphere trip this year as well. I hope that the TechQuest journey will illuminate and inspire you, as it includes fresh efforts such as TechSphere, the webinar platform, TechScribe, the creative articles platform, Tech Innovator, the podcast series, and finally Tech Narrator, the content video competition. Before we begin the program, I would prefer to walk through the TechQuest journey with you. Okay, the moment you are all been waiting for has finally arrived. The wait has finished. It's time to dive headfirst into our main topic for this program. Have you ever wondered what lies at the heart of our time's most baffling and mind-blowing technologies? Primary aim of quantum artificial intelligence is to improve human freedom, dignity, equality, security, and total well-being, says Amit Ray, acclaimed Indian author. Our adventure through this quantum realm is made even more exciting by the presence of a true luminary in the area of quantum computing. It's an honor to introduce our guest speaker, Mr. Priyal Valpita, who is at the forefront of quantum innovation and has made significant contribution to this cutting-edge field. Mr. Priyal Valpita is a true technology innovator known for his amazing expertise and remarkable journey across the digital landscape. His extraordinary career encompasses a variety of jobs, each distinguished by creativity, leadership, and unwavering dedication to excellence. Mr. Valpita is the current Chief Technology Officer at SciCon as a visiting lecturer at the University of Colombo School of Computing. He shared his skills and ideas with future technicians. Prior to this, he was the Chief Technology Officer at Sorosai Incorporated, the Chief Software Architect at Holmatic Technologies, and the Principal Architect at DP Technologies Private Limited. He is a lifelong learner with an extensive collection of certifications, including those in artificial intelligence, machine learning, blockchain, decentralized finance, software design, and architecture. His passion for knowledge continues to drive him forward. With his unparalleled expertise and thirst for continuous learning, we are honored to have Mr. Priyal Valpita with us today. Please join me in welcoming him to our amazing journey. Sir, it's over to you.
Yeah, thank you, Samadhi, for that nice introduction. I hope that everyone can hear me clearly.
Yes, sir, we can hear you.
Okay, and I hope you can see my screen as well.
Yeah.
Nice.
You can see.
Okay, so let's begin the journey. So these are the things that we'll be discussing. The classical computing and quantum computing, and some applications, some myths that we are having on quantum computing. some principles, types of quantum computing, and future prospects, and Q&A. So then again, guys, this particular session, it could be like, first of all, I want to tell you that this, I mean, it's a kind of computing, so it's kind of like a bit of a deep subject. So best to make it very simple for you. So then is it just a fast computer that we can have? So that is a question mark, right? So what do you think? So just hold on to your thoughts, and you can assume some answer into this one as well, and then let's move forward. So if you think that it is you can compare these quantum computers into supercar in this analogy, it is not, right? So supercar is here. So quantum, whenever that you are you cannot compare a
computers. There's something else entirely. And before we can even begin to talk about their potential applications, we need to understand the fundamental physics that drives the theory of quantum computing. We'll need to dive into another dimension, smaller and more alien than anything we intuitively understand.
Okay, so that is a very basic introduction about quantum computers. So as it says that whenever that we are coming to quantum computers, we are talking about extremely small objects. So then again, as I explained to you earlier, it's not a replacement but a complement, right? So nobody can say that whenever that the quantum the quantum leaps, or the quantum supremacy comes, that we need to throw away all our laptops or mobile phones and all, and then we will be using quantum computers. There's nothing like that. It's just a complement. Okay, so these are the let's talk about a bit of myths that I replace classical computing. Having in the universe is used to call as absolute zero, right? Just before then 0 Kelvin. But quantum computers are cooler than that, right? I will tell you why we need to cool these systems to that level as well in next slides, right? And then again, quantum computing is only for scientists and researchers. This is also false, because we are using these things for many other use cases today as well, even with its very limited capacity. Okay, so let's move from known to unknown. I hope most of you guys know how a classical computer is working, right? So let's have some comparison in between classical computing and quantum computing. So classical computing is mainly based on these bits, 0 and 1. Everybody knows that. But quantum computings are not like that. It is based on quantum bits, right? These 0 and 1 is mainly based on voltage levels. Normally it is if it is, we can say that if it is 5 volt, it is 1, and if it is 0 volts, 0. But quantum and computation model also is very different, because when it comes to quantum computing, it is like deterministic computing that we are talking about. When it comes to classical computing, what do you mean by deterministic? Deterministic means that if you input the same input to a classical computer, it will always give you the result that heads or tail, right? It's in both state. Sometimes it's in head and sometimes it's in tail, right? So so that's why that you are calling it a superposition. So whenever that the coin falls into the flow, or you take the coin into your hand, then we can tell, or we can say that the coin is collapsed. So then you can observe the state whether into heads or if you are a boy, you are asking out the pretty girl, right? So until that girl, in one given instance, it can be all in this 32, we observe it, right? So that is the main difference in between a classical state and a quantum state, right? So I'll give you another example. So let's see that how we can then solve this problem. I mean, if it is like, if it is has all, if the 5-bit quantum in 1 so what you need to do in a classical computer, that you need to start from here and like experiment all the possibilities up until that you reach here to find the password, right? So in this example, you have to try it like 11 times until you find the password. So if you know about little bit about the computing cost of this search, of this trying out, is called the in big O notation is ON, right? So because that you need to traverse through all the possibilities. But what will happen if you are doing the same in quantum computers, right? Right? There are certain algorithms such as Groover's algorithm that you can find the answer in quick instance. You don't have to go through each and every state, because a quantum computer can have, if it is a 4-bit quantum computer, it can have all these states, so you can input all these things into one at once into a quantum system. So I hope that you get some idea about the powerfulness or the computer power of quantum computers using this example, right? Now, don't get afraid. So this is why that I think you might have heard that, like whenever things like whenever that a quantum computer comes into to the market, that all the security algorithms and everything will get failed. Yeah, it can happen. So this is for that. But you need to have like huge, more than, like 1,000 or 2,000, 3,000 qubit quantum computers to achieve this. But as far as today, like the largest the quantum computer that we are having in Google is only 50, until that we achieve that kind of a computing power to break current encryption algorithms and all. But I hope that you get an idea. Okay, so the next, the quantum basic is called the entanglement. The entanglement means what? So this is like a very fascinating thing, right? So if you like couple two quantum particles, guys, mind you, like these quantum particles can be anything, right? It can be an electron, it can be an atom, or it can be set of atoms as well. It doesn't necessarily be only that need to like convert it into only to an electron or something like that. It can be anything, right? So if you like couple this kind of two quantum particles or qubits, right? So let's say one example, that always these qubits have like, whenever that you observe, let's assume that these two are qubits, that qubits are, right? So it's very fascinating thing if you study it further and further. Okay, the next quantum basic is called tunneling, right? So if you like assume that you are rolling this large rock like in a hill like this, that you are going into like classical or classical physics or traditional physics, that you need to like climb it, like take it up the hill and then take it down. But whenever that you go like when you zoom into the quantum level or into the atomic level or in the electron level, there's a thing called quantum tunneling, right? The quantum tunneling means that even if there is a barrier in between, these quantum particles can go through it, right? Like this barrier is not like it's not applicable to these certain quantum particles, right? So that is called quantum tunneling. So, and if you know a little bit about how the semiconductors are working, right? And that another thing is that like the Moore's law. The Moore's law used to say that every 2 years time the number of transistors in a chip or in a microprocessor doubled every 2 years time. But it has stopped like, around, I think, because these transistors are getting like smaller and smaller and smaller. And now I think, as I remember, if you take a latest microprocessor, the distance in between atoms away. So because of that, the electrons that are like going through or controlled in these transistors are used to have this quantum tunneling effect, because these things are too nearby to each other, these transistors. So you cannot have these these p-n blockades in a semiconductor. So that's why it's computers that we have achieved the maximum speed in single computing, but that you can have like parallel lot of chips or parallel microprocessors and attain speed, but is like achieved. I mean, like we are using these things as in their maximum tunneling as well. And the last the quantum basic that you need to understand is called the quantum coherence. So what do you mean by this quantum coherence? So I have explained all these fascinating things about this entanglement and all these things here, right? So all these things are possible. Hypothetical quantum bit, and you can program it in a way that the actual quantum bit or the qubit can behave, right? So these things are mainly for like for students to to simulate it, to see what is happening and all that. So these things are called quantum inspired computing. And this next one is quantum annealing, right? So quantum annealing, I think you might have heard about the D-wave quantum computer. So it is using this technology called quantum annealing. So quantum annealing, the quantum annealing is something like this. So you have this, you have this waveform of this quantum or qubits, right? So you are doing this, you inject another wave or another wave which is like same as the same, I mean, in the same frequency of this quantum qubits, and then you can observe the result. So there are some scholars saying that quantum annealing is not a real quantum computing as well, but it's like out for like debate. So these things are like mainly using for like in optimization algorithms, right? Especially like when it comes to quantum AI, or like finding the optimal solution. So those kind of an optimal algorithms that you are using these quantum annealing computers. So a real world example is a D-wave. So as I remember, this D-wave quantum computer is something around like 2000 qubit quantum computer. But having said that, this one doesn't have the power of as you example, like in our next quantum computer. So this one is the Google Sycamore quantum computer, right? So if you compare this thing and this D-wave, so the Sycamore quantum computer is much more powerful, even though that is a 53 qubits, because of the algorithms that it is using. So that's why that many people used to say that annealing quantum computers are not actual quantum computers, right? But it's there. Okay, so what do you mean by the gate-based quantum computing? So if like classical computers are all like operating based on gates, the AND gate, the NOT gate, the XOR gate, and all that. So this gate, the real quantum computers are also do have these kind of gates, right? So these gates are used to call this poly X, poly Z, Hadamard. If you do not know, a traveling salesman problem is that a salesman is there, that he needs to travel to all these cities and stop and do his or her sales. So the problem is that to find the optimal route right? The most fast and most optimal route to go this sales route, right? So this is a very, like common problem. So, I mean, like if you like see it in a very like, bird's eye view, you can say that, no, it's a very simple problem to solve. But like if you add up like, 30, 40 stops into this traveling salesman problem, it takes lots of computing power. I think if it is like more than 50, it takes like, years to solve this problem in using classical computing, right? But using annealing computing or annealing quantum computing, we can solve these kind of problems very easily. So what's the reason, right? So if this one is a physical lecture that I'm doing, I could have asked you the reason. So I'll give you the answer, right? The reason is this. So there are like a lot of routes in this, I mean, like a lot of solutions, right? I mean, like you can go in here to here to here to here to here, and like go like this, and go in a different path and all that. So why the quantum computer can solve this easily? Because the main reason is that if you are doing it in a classical computer, you have to take one route and like input it into a classical computer, and then we have to wait until like it gives the result. It's like deterministic, or like one by one that you need to input like all the results into that. But in quantum computer, it's not like that. You can take all the routes and input